There we go. Okay. All right. So thank you everybody for joining us today. Like Shannon mentioned, we're going to be talking about some alternative fertility sources for forage systems that are outside of kind of the usual, fertilizer additives that we think of when we think about forage fertility. And this topic is fairly relevant, particularly over the last couple of years as fertilizer prices have been increasing. So this graph is just showing prices for several of the major kind of fertilizer types that are used on agricultural operations from the end of 2020 through as of June of this year, so just last month. And you can see that, we had a drastic increase in the cost of all of our different types of fertilizers, throughout 2021 and into 2022, and they've started to level off a little bit now, but overall prices still remain a lot higher than they were, a couple of years ago. So basically within the last 2 years, prices are basically up as much as 76 to 84%, if you kind of do a little math, from where they were as of, the end of 2020. And here's just kind of a cost breakdown of some of those different nutrients based on the individual types. So nitrogen, phosphorus, or potassium. I just throw those numbers up there because we're going to use those a little bit in some calculations as we go through the presentation today and talk about, what these costs mean and how we can apply that to forage systems. So we know that even though fertilizer prices have increased over the last few years, that adequate soil fertility is still essential for our forage systems, right? So we know that we need adequate fertility for good forage establishment, for good root growth, to be able to uptake nutrients, to have a good yielding stand of forages, to minimize weed pressure, maintain the vigor of our stand over time, and to provide some resistance to things like drought or disease. So there's a lot of things at play when we think about soil fertility and supplying nutrients to our forage systems. And it's just as important for forages as it is for any of our other agricultural crops. So I like to think about nutrients and then in sort of a cycle. So we think about, we have a series of things going into that system, and we also have a series of things coming out of that system. So examples of things that would be kind of adding nutrients or contributing nutrients to that cycle would be kind of soil mineralization happening, fertilizers that we may be adding, manure, other feed or minerals that may be fed on our forage systems, nitrogen fixation by legumes, things like that are all contributing nutrients to that system. And on the flip side of that, for outputs, we have things like when we harvest forage, we remove nutrients, livestock or their products remove nutrients from a system. And then of course we try to minimize lost pathways as much as we can, but we do still usually have a little bit of loss happening in terms of nutrient losses. And so you see on here, fertilizer, of course, is one of our big inputs. And we talk a lot about fertilizer, and it's still very important. But given the high prices and, kind of sustained higher costs for fertilizer over the last few years, I wanted to focus more on some of these other things that we might not think about quite as readily as we think of adding fertilizer. So the problem when we have this cycle is when our inputs and our outputs start to get a little bit off balance, right? And we know that harvesting and grazing both remove nutrients from a system. We'll talk about the difference between those two types of systems here in a minute. But in general, when our outputs start to outweigh or become greater than our inputs, essentially what we're doing is mining that soil for nutrients, right? And while we can, continue to do this for a short time and might not see, a huge impact of that, over time, we're going to start, starting to see decreased productivity, decreased resistance of that stand, et cetera, et cetera. So that's kind of the system that we want to avoid. We want to keep that nutrient cycle in balance. So I've mentioned that both harvesting and grazing forages removes nutrients, right? In a hay production system or any harvested forage system, we're removing a very large percentage of the nutrients present in those forages, right? So up to 80% on average of the nutrients are coming off with that hay crop or with that forage crop. On the grazing side of things, we have much more of that cycling happening. So we have a less removal overall. So, and this is because a large portion of what is going into those animals as they're grazing those forages is also coming back out the other end, right? In terms of manure, urine, etc., that gets deposited back on those fields. So we have more of that cycling happening naturally in a grazing system than we do for our harvested forages. And just to put some numbers to that, here we have kind of an example comparing a hay production system versus a system with cattle on pasture. And if we consider these on an equivalent land basis, so say we have equivalent land basis, 1 acre for each of these systems. If we're harvesting, say, a 3-ton crop of hay, we're removing on average 150 pounds of N, 22 pounds of P, and 155 pounds of K with that hay crop as we cut that and remove that from that field. If instead that same field were to be grazed instead of harvested for hay, and we would instead remove the beef from that we produce from that field instead of the hay, we would only be removing around 16 pounds of N, 5 pounds of P, and a little over 1 pound of K. So you can see the big difference there in nutrient cycling between a harvested forage system versus a grazing system. So we're really removing a lot more with those harvested forages. So here's just a chart showing some of our common forage species and looking at, on average, the amount of nutrients that they're removing in terms of pounds per ton. So you can see that for really all of these common forage crops, they are removing a large amount of nutrients. And the key here also is the pounds per ton. So the more productive a stand is, the more forage we're producing from that stand, the more nutrients we're removing when we remove that forage crop from that field. So a higher yield equals a higher nutrient removal. And that means in turn that we need more nutrients to be replaced to sustain that yield, right? So if we want to maintain that high productivity, we're going to have to be replacing those nutrients in some way, shape, or form. So if we put a little bit of numbers to this, and we kind of take some of those averages that we looked at just from that previous chart, and we assume 1 ton of hay is probably like a standard grass hay, we're going to be removing, or contained in that hay, have 45 pounds of N, 15 pounds of P2O5, and 55 pounds of K2O. I just pulled those numbers as kind of an average from that previous chart. And we look at the cost of those nutrients. So this is where we're pulling in those numbers from that very first slide where we looked at the cost of each of these nutrients on a nutrient per pound basis. So we have 68 cents per pound for N, 64 cents per pound of P2O5, and 51 cents per pound of K2O. And I updated those just earlier this morning, actually, based on the June 2023 values. So they should be fairly current. And so if we're removing 1 ton of hay that contains those amounts of nutrients, and that's the cost of the nutrients, we can calculate a dollar value per ton in nutrient value that we're removing with that hay. And based on these numbers, we come out to around $68 per ton in nutrient value that we're basically removing off that field with that hay crop. So what does this mean? It means that we need to prioritize nutrients and prioritize kind of maintaining that nutrient cycle for our hay fields, especially because we're removing a lot of those nutrients with every cutting or every harvest that we take off. And of course, we are removing some in a pasture as well, but to a much lesser extent. So what do we do with that? Well, we know the systems are different, right? We know the pros and cons of each type of system. Regardless of that, we need to know what we have present in our soil, right? So this is where I'm going to tell you if you haven't already, go out and take your soil samples, figure out what is currently present in your soil, figure out what fields or what pastures might be high or low, what fields or pastures might be deficient or adequate in terms of forage nutrients. We're not going to really have time today to talk about all of the different essential forage nutrients, but there's just a chart with kind of the major macro and micronutrients that are essential for forages for growth and production. Of course, nitrogen, phosphorus, and potassium are the big 3 that we talk about a lot because those are the ones that are needed in the highest quantities by forages, and they also typically become the most limiting for our forage crops. But there are other nutrients that we can think about as well. And then, of course, we know that without a test, we're really just guessing at what's present in our fields, right? So there's your plug for taking your soil samples and keeping those up to date. And one of the things that I encourage you to look at, if you're not already looking at for with those soil samples, is not only the nutrient concentration in those different fields or pastures, but also the pH of that soil. So we know that our soil pH is affecting the utilization of our minerals. And what I mean by that is, if you look at the chart on the right over there, you can see a range of acidity and range of alkalinity. So we're going from a pH, a more acidic pH of 5, all the way up to a more alkaline pH of 9. And each of those black horizontal bars with the different nutrients listed is showing the availability of that nutrient at that given pH level. So you can see that as pH is changing, even if a nutrient is present in the soil, whether or not it's available to the plant is changing based on those different pHs. So as we move into more acidic conditions, so as we move further to the left of that chart, some of our essential nutrients, things like phosphorus, calcium, magnesium, are still present in the soil, but become a lot less available for those plants for uptaking them under those more acidic conditions. At the same time, some of our other nutrients like copper, aluminum, iron, ones that maybe have at times potential for toxicity, tend to become more available under those acidic conditions. So the more acidic our soil gets, the more we're kind of reducing availability of some of the essential nutrients that we want to be supplying, and increasing the availability of some nutrients that might be prone to being in excess. So for most of our forage crops, we're kind of looking to stay in that optimum pH range of somewhere between 6 and 7 for many of our forages. And you can see that, you know, at that range, which is between those two yellow lines, we have pretty much optimum availability of many of our essential forage nutrients. So that's kind of where that ideal range comes from. So if we put some numbers to that, and we think about nutrient availability in terms of cost, we just said that we can have a decrease in the availability of those nutrients as our pH decreases. And it can be a pretty significant amount. So this is showing a difference in a soil pH of 5.6, so kind of more acidic, a little bit outside that ideal range, versus a soil pH of 6.2. So a little bit more neutral, more in that kind of ideal 6 to 7 range. And what you see here is our three major nutrients, so nitrogen, P2O5, K2O, and just kind of plugged in some numbers for an annual use. This is average. You can change these numbers for whatever based on your own operation. But if we're saying for this example, we're using on average annually 200 pounds of N, 50 pounds of P2O5, and 150 pounds of K2O per acre for the year. And we applied those same price numbers that we looked at in the beginning from that fertilizer graph. So 68 cents, 64 cents, and 51 cents for each of our nutrients. Then our fertilizer costs for the year would be around $245 per acre. And so that would be kind of the ideal, right? That's what we're applying. Well, if our soil pH is more acidic, so that if we move down to that 5.6, and we have a decrease in availability of each of those nutrients, so we're applying the nutrients, but they're not necessarily available to the plants, we see a decrease in efficiency, so a decrease in the availability of those nutrients, and we can subtract that and kind of just assign, you know, also a dollar value. And for this example, it's about $72 per acre that we're essentially losing. You know, we're still applying that fertilizer, but because it's not available to the plant, it's essentially, you know, a wasted application, right? So we're losing, you know, close to, what is that, a third or so of what we've applied to those plants. So just by changing the pH, we can increase the availability of our nutrients. So my point here is make sure to look at your pH on your soil tests, make sure we're applying lime accordingly so that we can kind of maintain a good soil nutrient availability for our plants. And then the other thing about soil pH is not only does it affect the availability of nutrients, but it also affects root growth and root development. So here in this figure, you can see pictures of root establishment under different pHs. So pH of 6.5 on the left. So more of an ideal pH. You can see we have longer, healthier roots, more branching of those roots. And if we are in a more acidic soil conditions, either 5.2 or 5.5, you can see those roots are a lot more stunted. So those roots under those more acidic conditions are not going to be able to extract nutrients and water from the soil as well. We're going to have less soil mineralization happening, less nitrogen fixation, kind of overall less nutrient availability. So pH is really important to kind of keep our nutrients available to our plants and keep that root growth happening and keep those strong, healthy roots. All right, so what about other sources of fertility? So manure is one that first comes to mind to a lot of people, right, as a source of fertility. So we know that manure is a valuable source of many different nutrients. So here is just a chart showing some of the nutrients that are available in manure and also kind of a little bit on their role in plant growth. So you can see manure can supply, nitrogen, phosphorus, potassium, sulfur, calcium, magnesium, and other micronutrients as well. And those are all important for our plants, and they all fall under those kind of essential nutrient category. We can also measure the nutrient content in our manure. So this is just a figure that I pulled that's showing some average nutrient contents of manure for different groups of species and different manure types, so liquid versus solid. And if we look at the nutrient content, I know this is a lot of information, but just kind of looking on average across the board, we see that usually poultry manure, poultry litter contains on average kind of the highest concentration of nutrients compared to, other livestock species. So poultry and swine are usually on the higher end compared to cattle manure. But the other thing to think about with manure is you can see for each of these bars, those little colors are representing different nutrients in that manure. So we have total N, ammonium, total P, total K. And not only does it differ by species, but it also differs by, liquid manure versus solid manure. And in particular, if we look at the ammonium, so kind of that bright orange color, you can see that when we go from a liquid manure to a solid manure, we see a big decrease in ammonium. And this is important because ammonium is one of the most volatile components for as far as nutrients are concerned. So it's one of the ones that's more prone to losses when we apply a particular liquid manure on a field. And we'll show an example of that in a second. But just wanted to point out that, solid manure may contain a little bit less overall, but it also usually contains nutrients that are a little bit more stable or less prone to volatilization compared to the liquid manure. So we can use these nutrients in our manure to kind of offset those fertilizer expenses because like we said, manure is a good source of nutrients. And this is some more numbers just showing some averages, this time kind of specific to Maryland. So this is from the nutrient management program at University of Maryland. They have some average numbers, just like the previous one, but just looking at the numbers this time instead of on a bar graph for our various nutrients present in these different types of manure or litter. And I just wanted to pull out an example to show kind of the dollar value that some of these can provide. So for this example, we're going to look at a solid cattle manure. So if we're taking cattle manure that's solid, not in liquid form, and we're spreading that on a field, on average, we're looking at 0.77% of that is going to be nitrogen, 0.42 for P2O5, and 0.9 for K2O. And you may look at that and at least, in my mind, I say, okay, those are all less than 1% of each of those nutrients. So is that even worth it? Is it even worth, spreading when we're looking at as a total, we're only applying less than 1% of a nutrient? Well, if we look at how we're actually applying those, most of the time we're applying them in fairly large quantities, right? So like 10 tons per acre or something like that on average. So if we calculate that out and we're applying 10 tons per acre of a solid cattle manure, kind of average values, then we are come back out here. Sorry, hold on. Okay, there we go. Then we are essentially applying on that field 154 pounds of N per acre, 84 pounds of P2O5 per acre, and 180 pounds of K2O per acre. So you can see when we actually calculate it out, it becomes a lot larger than just, when you're looking at less than 1%. And if we take those same expenses per nutrient that we've been using for the whole presentation, we end up with a total fertilizer value from that application of $250.28 per acre. So you can see it is a significant savings and is a significant source of nutrients for our forages. The other thing with manure, so I mentioned differences in volatility between our different types of nutrients. So there's been a little bit of work here in Maryland looking at ammonium volatilization on some farms who are applying manure. And for each of these, across the bottom, you see there are a couple of farms from Carroll County and a couple of farms from Frederick County, Maryland. And the farm numbers, you see, 1, 3, 1, 2, 3, those are different farms. And for each of those farms, they're doing two different treatments. One is where the manure has been broadcasted across that field. And the other is where they're actually injecting that manure. So it's being applied basically into the soil or kind of subsurface, not just being broadcast on the soil surface. And what this is showing is at various time points, they're measuring volatilization or loss of ammonium basically from those different manures. And you can see for every single farm, we have a huge reduction in volatilization or in nitrate losses based on for the treatments that were injected versus broadcast. So I realize it's not always an option, but if it's possible to either incorporate or inject manures rather than spreading them on the soil surface, we can minimize losses that way. We can minimize volatilization. We can also, which wasn't really measured in this study, but we can also minimize runoff potentially from those different manures. So if it's an option for you, might be something to look into to kind of get the most of those nutrients present in your manure. The other thing with manure and nutrients is the temperature. So we want to be able to apply those nutrients when our temperature is
our lunch.
We want to be able to apply those nutrients when our temperature is lower because we have less nitrification or less volatilization. So in this graph here, you can see that as soil temperatures are increasing, we have an increase in nitrification. And so if we can apply manure when we have cooler temperatures and not quite as hot out, we'll typically see a little bit less losses and we'll be able to retain more of those nutrients in that manure. Also thinking about manure, but from a different perspective, we can think about it in terms of nutrient distribution. And especially for a grazing system, where we're not necessarily taking that manure and spreading it out in the field. I would argue that our grazing management plays a big role in how those nutrients are distributed. And so usually when we look at, animals on a pasture, we think of the animals themselves as kind of the dollar value, right, from that pasture, which is still true. But I also encourage you to consider that the manure from those animals also contains a high dollar value that can be applied to the pasture as well and can, turn around to produce more forage and apply nutrients and all that type of thing. But the question I ask is how uniformly are we distributing those nutrients across the pasture? I don't know, if you've seen a field that looks like this. I'm sure many of us have. We can see, little dark spots throughout the field, oftentimes, which is where a manure pile was deposited or where an animal urinated and it deposited nutrients on that field in that spot. And you can see a flush of forage growth as a result of that. And so we oftentimes in livestock operations see a lot of congregating. So we see that those animals are tending to congregate, whether that's under a shade tree, whether that's around a waterer, whether that's, near a gate possibly. And so essentially what those animals are doing is grazing throughout that field. And then consuming all of those nutrients. And when they come back and congregate in the shade or around the water or whatever, they're redepositing those nutrients in that spot, right? So we can get hot spots of manure in those areas rather than kind of throughout the field on an even basis. And so they've done some work looking at how grazing management plays a role in this. And they've looked at different rotation frequencies. So whether you have a continuous pasture where animals have access to the whole field, compared to if you kind of subdivide your pasture and move the animals around, or if you make that even tighter and do a smaller area, more frequent rotations, and how many years it actually takes to get an even manure distribution, aka one manure pile per square yard of that pasture. And in a continuous system, usually this is where I make people guess how many years it takes to get one pile per square yard. But it usually shocks people that it's around 27 years to get one pile per square yard under that continuous system. And that's because those animals are congregating and going back to their favorite places in the field over and over versus kind of being more evenly distributed throughout the field. And so by using more rotational grazing, by moving those animals around to different areas of the field, we can really reduce that and start to get more of an even distribution of manure, aka more even distribution of manure nutrients, right, across that field. And so what that might look like is something like this. So in the top figure there, you can see that this is just one paddock if there's a 3 pasture rotation. So a larger area, a larger pasture space given to those animals. And you can see we have a few maybe hot spots kind of over on the right there in the bottom left corner where we have a little bit more dense manure in those areas, but overall kind of a low amount of manure throughout that field. If we were to tighten that up and instead do 24 different pastures, basically a more intense rotation, give those animals a smaller area for a shorter period of time, we really increase the amount of manure piles we get across kind of that whole area. So we're kind of evenly spreading that out through the whole field and increasing the density of the manure across that whole area. So I encourage you to also use not only your manure, but your hay as a nutrient source. So if we, this is the same slide we saw earlier. So 1 ton of hay contains those average nutrients. We're using the same cost for those nutrients. We said earlier, kind of, we can calculate out that dollar value of $68 per ton in nutrient value. Think of your hay not only as an opportunity to get feed for livestock, but also as a source of nutrients. Remember, we said that harvesting hay or removing hay from a field is removing a lot of nutrients. So if you're purchasing that hay or bringing in that hay or feeding that hay, you're feeding not only the animals, but also a lot of nutrients, right, across that field. So you can use book values like what I just used in the previous example. You can actually also calculate the total N, P, and K content on your hay specifically. If you have a forage analysis and you take a forage analysis, you would use the numbers for crude protein, phosphorus, and potassium. You would get the percentages off the forage analysis. You could calculate that out into pounds per ton, and then use these conversion factors to get pounds of each of those nutrients per ton. So just a fun fact, fun tidbit, if you want to get really exact with it or start, kind of individualizing it a little bit for your situation specifically, you are able to do that. And just like for grazing, how we feed our hay also matters, and it affects how those nutrients are being distributed across that field. So here is a screenshot of some soil samples that were taken in North Carolina at one of their research centers where they have the beef cattle field lab. This is of a pasture where some cattle were being housed and they were being fed hay. And what they did was they took grid samples. So every single one of those orange dots is an individual soil sample. And this figure is showing what the soil phosphorus levels at those individual grid spots were. So the larger the circle, the bigger orange circles represent a much higher concentration of phosphorus, and the smaller the circles represent a much lower concentration of phosphorus in the soil at those places. And so who wants to guess where they were feeding their hay in this field? It's fairly obvious when you look at it like this, right? We can see these 3 spots in particular have a lot higher concentration of phosphorus. So those happen to be where the hay was being fed, probably because it's close to the road, close to gates, close to having easy access to bring hay in. And you can see that we have a lot higher phosphorus concentration there as a result. Versus on the far left side of the pasture, we have much lower phosphorus concentrations. So think about this in terms of you can feed hay on your poorest pastures or fields. So the pastures or hay fields that need nutrients, if it's possible to feed hay on those fields, we can add nutrients in that way. And also think about if you can, or if you have the ability to do so, moving our feeding spots around. So we're not always feeding hay in the same areas and applying more nutrients to those spots, but rather kind of focusing on that distribution and making it a little bit more even. And so this is a very similar concept. Here was a project in Missouri where they were again looking at hay feeding management and how uniformly nutrients were distributed as a result. And so here they compared a stationary ring, so just hay feeders that were not moved throughout the experiment. Then the middle one is moving those ring feeders across the field, kind of in sequential order. And then the bottom one was actually unrolling hay and really kind of spreading nutrients out. And you can see on the left-hand side, all of those little green dots represent basically manure piles that were deposited in those different fields. So you can see the concentration of manure was much higher, of course, where the stationary ring was in the top, versus as we move down, we kind of start to see more even distribution of that. And then on the right is just some aerial images kind of showing that same sort of thing. All right, so we've talked about manure, we've talked about using hay as a nutrient source. Legumes is another one that can supply nutrients, right? So we know that legumes have the ability to fix atmospheric nitrogen. And this is due to that symbiotic relationship with rhizobium bacteria in the soil. And different legume species and also different productivity levels can affect the amount of nitrogen fixed, but really they can fix anywhere from 50 to 300 or even more pounds of nitrogen per acre per year. So they have a big advantage in terms of fertility compared to some of our grass species. And just a fun fact, this image on the right is showing a picture of a legume with the nodules on the roots. So that's where those rhizobium bacteria live, and that's where this, nitrogen fixation process happens. And if you are to cut one of those little nodules open, what you're seeing in the bottom right there is the inside of a healthy root nodule. So it should be that bright pink color, which shows that it's active and healthy. If it's, a pale pink or white or kind of shriveled up, then it's not necessarily an active one. So just a little fun tidbit for you there. And like I said, the amount of nitrogen fixation will depend on what species we have, the growing conditions, all of that stuff plays a role in how much nitrogen those legumes are supplying. So one thing that many people don't necessarily realize is that nitrogen that is fixed by legumes is shared indirectly. So it's not like legumes are fixing nitrogen and then saying, here, neighboring grass plant, have some nitrogen. I have extra that I've fixed and I'll give it to you. So there's not a lot of really direct sharing. And the other thing to consider is that those nodules, which are again, below the soil surface with those roots, we think of them as the factory, right? So they're producing that nitrogen. They're not the warehouse. So that means that they're not the main site of storage for that nitrogen. So most of the nitrogen in a plant is actually found in the top growth, so above the soil surface. So we think about kind of different ways that a legume plant is, sharing or adding nitrogen into a system. We have a direct transfer through mycelial networks, which is very minor. So there's a little bit of transfer happening, but it's not the primary way that grasses and other forages can get this nitrogen from legumes. We also have dead roots, dead nodules, sloughed cells that are decomposing in the soil. And as they decompose, they're releasing some nutrients. So this is kind of our secondary contribution of nitrogen from legumes to some of those grass species. But really the primary way, or one of the best ways to get these legumes to share their nitrogen, is by grazing a system, or having those above ground herbivores which consume that top growth, which is where a lot of that nitrogen is found. And then as those animals are going to the bathroom and adding manure and urine into that field, then that is a source of nitrogen that can be broken down and uptaken by non-legume plants. So there's a lot of different ways that nitrogen is shared, but just remember that it's not just a direct share from legumes to grasses. There's all of these different complex processes that are happening for that to occur. So we've said that legumes have this ability, and we said that it can be a cost-effective way to add nitrogen to hay and pasture systems. So again, I wanted to kind of put some numbers to that. So if we take some of our primary legume species, so alfalfa, red clover, white clover, some of the annual clovers, and we look at, on average, the amount of nitrogen that they can fix for kind of your average healthy stand. You can see the range there in pounds per acre per year for each of those. So that's how much nitrogen those different plants can fix. And if we apply our same dollar value for nutrients, so this is the numbers that we used to use pretty regularly when nitrogen was a lot cheaper, when it was more like 40 cents per pound for urea nitrogen, then we would be looking at a dollar value from anywhere from 20 up to 120, depending on the species. Nowadays, when nitrogen prices are a lot higher, if we look at our more current prices for 68 cents per pound, we can see, of course, that those dollar values are increasing. So we're looking at anywhere from $34 to $200 per acre per year if we try to, put a dollar value on the value of that nitrogen that's being fixed by those legumes. So you can see it's a very substantial amount of nitrogen that's being fixed by the legume species. The other thing to remember is that it is a function not only of the species, but also of the yield or the productivity of those different species. So here you can see some different figures for white clover, red clover, and alfalfa. And for each of these, the graphs are showing the nitrogen fixation on the x-axis or y-axis related to the total yield. So you can see that there is a relationship for all the species, where as our yield is increasing, we have more nitrogen fixation happening. So I put this out there to make the point that, a lot of times we get those little white Dutch clovers or little volunteer clovers that are just really tiny, and they kind of fill in some of the bare spaces in our fields. And while that does have some value, those really probably are not fixing very much nitrogen. So what we need, if we're going to rely on legumes for fixing nitrogen, is a good productive stand that's producing yield and is actively kind of fixing that nitrogen. So increase in yield equals increase in nitrogen fixation for our different legume species. So then the next question that often leads to is, well, how much legumes do I need to have this relationship and to have some nitrogen fixation from my legumes? And the answer to that is we like to see the legumes make up about 30% of the sward on average to have kind of a substantial contribution to the nitrogen fixation pool. And the key word there is 30% of the sward by weight. You can see weight there at the end. So if I were to ask you just briefly to kind of look at this picture and say what percent of clover, what percent of legume do you think is present in this stand? I would guess a lot of you would be thinking, at least 50%, maybe more like 75, 80%, right? Visually, it looks like there's a lot of clover in that within that white square compared to grasses. If we were to actually, and this was done, if we were to actually clip that square, all the forages inside that square, separate out the clovers and the grasses from each other, and weigh each of those components by weight, we actually have only 25% legume, 75% grass, and then there was 0% weeds in this one. And so I say this to illustrate that sometimes it can be deceiving, especially with clover. It has those wide, broad leaves, and it might look like there's a lot of clover out there, but oftentimes if we actually weigh it, there tends to be less than what we're thinking there is, just looking at it visually. And then here's another one. This one, of course, is one that's a little bit taller, a little bit more later after a harvest or after a grazing. And this one has 30% legumes, 68% grass, and then 2% other things. So again, a little bit kind of deceiving just visually looking at it. Although I think in this one, the visual representation kind of more closely matches what actually is there. The key difference here is the main difference between these two pictures is the total amount of forage, or the total height of that stand, the total amount of forage. So when a stand is just regrowing after grazing or after clipping, I think the clover can oftentimes be deceiving. We have less grasses that have filled in, a lot more clover leaves that we can see, versus if we, wait a while, sometimes we can start to see those grasses kind of grow taller, cover up some of the clover, and be a little bit more visual. So just wanted to throw that out there just to keep in mind that really it's what we're looking for is by weight, not just by kind of what it might look like visually. And then the other thing to remember, if you're trying to keep legumes and favor legumes in your stand, that whenever we fertilize with nitrogen, we're skewing the stand more towards grasses, because the legumes are able to produce their own nitrogen. So if we have less nitrogen fertilizer, we're kind of making those legumes have the advantage because they have that ability to produce that nitrogen, versus if we are adding a lot of nitrogen fertilizer, we're kind of shifting the advantage over to the grasses. And the opposite is true for the phosphorus and potassium. So if we're kind of fertilizing more or focusing on keeping our P and K fertility up, then we're going to be starting to favor more of the legumes and favor the grasses a little bit less. So you can use your fertility strategy and your fertilization to help maintain a larger grass component or larger legume component, kind of as you want it to be. And then I just wanted to mention, we're obviously not talking about how to plant things here today, but if for those who might not be familiar, if you're trying to add more legumes into a stand, we can obviously drill those in. We can include them in seed mixes when we're establishing stands. But another easy way, especially for clovers, is to use frost seeding, broadcasting that seed on the soil in the late winter and kind of letting that freezing and thawing action work that seed into the soil and kind of boost the legume component of our stands. That's a really common way to add some more legumes into an existing stand. All right, the other thing that I wanted to mention was using annuals as a means of fertilizer. And this may sound a little counterintuitive. There's a lot of reasons that we like to use annual forages in a stand. We're focusing obviously on the soil side of that today, but we know that annual forages come obviously in a lot of varying shapes and sizes. So there's a diverse array of annuals we can use. A lot of them have some soil penetrating roots, especially some of our brassicas or more tuberous crops. We have that thick taproot and that deep taproot that can go down deep into the soil profile. They can be used, of course, to increase the organic matter of the soil, help a little bit with compaction. And then the key one that I wanted to focus on is nutrient uptake. So there's been some work done by Ray Weil here at University of Maryland looking at the nitrogen uptake from cover crops, in particular for radish. And I'll try to explain this figure a little bit. So on the y-axis on the left there, we have soil depth. So we went from 0 to 180 centimeters deep into the soil. So that's about 70 inches for those who think a little bit more in inches versus centimeters. So he measured at all of those different soil depths. He measured nitrate nitrogen concentration in the soil. And he did that under no cover crop, which is the brown line that you see, and then under two different types of radish, which are the two green lines. And what you can see from this figure is as we go deeper into the soil profile, with the no cover crop, we saw a big spike in nitrate nitrogen when we were, around 80, 90 centimeters deep. And we saw another big spike in nitrate nitrogen present when we were further down, like 170, 180 centimeters deep. And we did not necessarily see these big spikes with the radish cover crop. And so what he has surmised from this is that under those radish cover crops, those deep penetrating roots are going really far down into the soil profile, and they're actually pulling some of that nitrogen deep up from the soil back into the top growth. Remember, we said a lot of nitrogen is, stored in the top growth of the plant. And so they're helping to pull some of that deep nitrogen up from deeper in the soil profile and kind of bring it back to the surface or back to the top growth where we were able to use it. So kind of an interesting thing, different way to think about using annuals in a forage system. A lot of our different annual species can be used kind of to maybe accomplish something like this, as well as offer other benefits. All right, and then the very last thing that I kind of wanted to mention for kind of an alternative thing to think about is soil mineralization. So we know that naturally all of our soils within the organic matter contain nitrogen, and the higher a soil organic matter level is, the more nitrogen is contained per acre, of course, because we have more organic matter. So more organic matter equals more nitrogen present in that soil naturally. The problem with that is a lot of that organic nitrogen is very tightly bound. So what we need is soil microorganisms to have that mineralization process happening and make that tightly bound organic nitrogen become plant available. So PAN, plant available nitrogen. So we want that mineralization so we can basically free up that organic nitrogen and make it available to the plants. And the problem with that is it's really hard to assess how much of an organic nitrogen pool is stable versus how much of that is biologically active, or how much of that is going to become available to plants. So we can measure, the total amount, but we don't necessarily know how much is stable and how much is actually going to be available to a plant. And so if we can, of course, we would want to make that biologically active pool more available to the plants without, of course, overdoing it and having nitrogen losses. And so there's been a researcher down in North Carolina, Dr. Franz Lubers, who's kind of been studying this a lot over the last several years. And in particular, I wanted to just mention really quick this project that he's looking at, because I think it's showing some interesting results that are promising for kind of capturing this. So he's been looking at some on-farm tall fescue fields all across kind of the southeast US. So North Carolina, Virginia, West Virginia, South Carolina, Georgia, 92 sites. So a lot of different sites, a lot of different farms that they're measuring this on. And what they're doing is comparing nitrogen mineralization of that soil organic matter against nitrogen supplied by urea fertilizer at several different rates. So how does that organic mineralization compare to applying urea fertilizer? And on average, the yield did improve with higher rates of nitrogen fertilizer. This is why we have recommendations for applying nitrogen fertilizer, right? Because we can boost our yield. The interesting thing, though, was that he found, and granted, this was done over the last, 5 or so years. So some of this has been done when nitrogen prices were higher. But interestingly, only 28% of the sites has had sufficient yield increases to cover the nitrogen cost. So if you actually look at the economics of it, only 28% of the time it actually paid off to apply that nitrogen. The other 72% of the time, they really didn't need to apply that nitrogen in terms of kind of total economics or boosting their yield. So they already had optimal production. And so the question is, why is this, or why is this happening? And the theory is that some of those fields had a higher nitrogen mineralization happening in that organic matter pool. So they had more mineralization happening. So those forages were able to access more of that nitrogen from that natural kind of mineralization process. And so we know that different types of soils and different fertilities of soils and different, textures and management systems all play a role in nitrogen mineralization. And greater mineralization means we have a greater ability to supply plants with that available nitrogen. So the downside of this is determining that mineralization potential is a very long time-consuming procedure in the lab that takes like 2 months of processing. And so by the time you do it, it's changed, right? This is something that's always changing. So we really want something or need something that is a way to capture this in a quicker, more efficient way. And what he is finding is that a lot of the soil health tests that you see starting to become a little bit more prevalent at different labs, they measure soil biological activity. And what he's done is compared this soil biological activity test against the soil mineralization. And when you compare the two, you can see a strong relationship. So there's a positive relationship between that natural mineralization process and the biological activity happening in the soil. And the advantage is this biological activity test is very quick, very easy, a super fast thing that we can do that doesn't require that like long, lag of processing. So where he's going with this and where the kind of group is going with this is if we can measure soil pest biological activity, and we know our soil is more active, there's more soil biology, we can sort of assume or know that there's this positive relationship between that and the mineralization that's happening in the soil. And so what they're proposing is, this is kind of our standards when we think about nitrogen application rates. We want to optimize production, right? So we want to apply 100% of what we need to maximize productivity. And what they're suggesting is maybe instead of always applying to meet 100%, we can kind of adjust that. And as our soil biological activity increases, as we get a higher value for that, we can decrease the nitrogen that we need to apply. So hopefully I didn't overwhelm everybody with that. This is kind of a new area. But I really wanted to mention that to show that there are these other things that people are working on for ways we can kind of get about looking at not only the fertility or the chemical side of our soil, but also maybe the biological side and how that plays a role in this as well. So with that, I'm just going to wrap up by saying that remember that our soil is a very dynamic ecosystem. So we do have, physical, chemical, and biological components in the soil, and following the soil health principles that you may be familiar with, things like minimizing soil disturbance, maximizing soil cover, increasing biodiversity, making sure we have continuous living roots in our soil, integrating livestock, all of those things can work to improve not only the physical or chemical, but also the biological component of that soil, which may help kind of with our overall soil health and overall kind of nutrient availability in our soils. So when we think about kind of fertility inputs for forages as a whole, we do still have, of course, our fertilizer as a tool in our toolbox, as an effective way to apply nutrients where needed. We also have manure that can either be spread on the field or applied through grazing livestock. And again, remember, if we're going to be grazing, we want to be ensuring even nutrient distribution as much as we can. We can also apply fertility in the form of hay, and where we feed that hay on different fields can have a role on how we are applying fertility within that system. And then we also have the value of legumes in nitrogen fixation and some of those kind of diverse forages, annual forages, working to kind of improve the biology of our soil to kind of capture more of that natural mineralization process happening. So we have a wide array of tools in our toolbox, if you will, in terms of fertility, ways that we can provide fertility for our forage systems. So with that, that was everything that I had for today. I did want to just throw up my contact information on there. If anyone has, questions or wants to follow up, we can, of course, address some questions now, but if you think of something down the road, feel free to reach out and I'm happy to answer questions. I do see one question in the chat. Does grazing versus broadcast also help reduce runoff? And yes, I would say, I mean, I don't have numbers to give you directly on this, but usually when we're grazing, we're applying, smaller quantities over kind of a larger area, and we're applying little quantities at a time versus broadcasting a large amount at a time. And also when we're grazing, we're usually applying manure in more of a solid form compared to sometimes, liquid manure that's being spread on a field, which has the most potential for volatilization, but also runoff as well. So grazing can have an advantage in that sense as well. And I see another question. Can you help us come up with a rotational grazing plan, or who can we reach out to? And yes, we're happy to help myself or as well as the rest of the extension team here in Maryland, we're always happy to help people if they're looking to either start rotational grazing or work on improving their system and kind of maximizing that. So yes, feel free to shoot myself or one of our team an email and we can definitely help you with that. All right, if there's any other questions, I'll hang out just for like a minute or so. But if not, thank you all so much for tuning in today. Like Shannon said at the beginning, we will be posting the recording on the Women in Ag YouTube channel. So feel free to kind of refer back to it there. And I will also send Shannon a copy of these slides so she can send those as a follow-up as well. So thank you all for tuning in and joining us today.